Okay, so here then, guys, is where we're going to wrap up the unit. You understand your tests are on Monday. But what we need to do to wrap up the unit is we need to finally be able to answer the question, at what conditions, what makes a reaction spontaneous? We understand that spontaneous means it happens on its own without any interaction from the surroundings. It doesn't need pushed, it just goes. So what makes a reaction spontaneous? So guys, what I'd like to do to approach this is I'd like to kind of get us to group around some of the common understandings that we have, then talk about the tension that exists, and then talk about finally how to resolve that tension using the concept of Gibbs free energy. Now guys, along the way, you are going to need to have readily available page 809. So guys, open your books to page 809. Because we're going to need to have that ready to go. So guys, generic understandings about spontaneity. What types of processes tend to be spontaneous? What denotes processes that tend to be spontaneous? Go ahead. They tend to be exothermic. Guys, are we in agreement on that? Guys, that things that are exothermic tend to happen on their own. That's why nails rust. That's why methane burns. Guys, that's why most processes are spontaneous, because they're exothermic. But then, guys, we had this weird experience. Some of you experienced this in lab today as well. We had this weird experience that there are some things that are endothermic and yet spontaneous. And how did we explain that? What makes this go? Go ahead, Doug. Say it again. And be more specific. What about entropy? Good. And wow. Well, that increases energy. Decreases energy. Yeah, so this is losing energy in the form of entropy. We're still losing energy. It's not energy in. Just like exothermic is a loss of energy, the energy of this is decreasing, but it's being lost in the form of disorder. So we've got an increase in entropy. And that's a driving force as well. You guys okay on that? Okay, so now guys, we've got a tension because we understand that there's an interplay between releases of heat and releases of entropy or disorder, an increase in disorder. So guys, the question then becomes this: what if these things are in tension? What if we've got a reaction that is endothermic? Well, then the only way it can be spontaneous is if it increases disorder. But how much does it have to go up? And guys, what if we've got a process that decreases disorder? How much energy does it have to lose in order to be spontaneous? Do you see the tension? And guys, that's what Gibbs free energy allows us to talk about. So this then is how we're going to wrap our arms around this. Guys, here's what we know. This is great summary for everything that we've done up until now. So all spontaneous reactions, first of all, tend to have large negative enthalpy values. They tend to be exothermic. But guys, in addition to that, there's an entropy component. That spontaneous processes also tend to increase entropy. And guys, if we've got a reaction that increases entropy and releases heat, that thing's going to be spontaneous. And if we've got a process that takes in heat and decreases entropy, that thing is not going to be spontaneous. But what if they're in tension? Well, guys, in order to resolve the tension, we need a factor. We need a relationship that brings together enthalpy and entropy. And guys, that thing has a name. That factor has a name. It's called Gibbs free energy. Sadly, over time now, they've dropped the name Gibbs, and you may just hear it called free energy. Either one of those is acceptable. But guys, here are the fundamentals of Gibbs free energy. First of all, Gibbs free energy is a thermodynamic function. It's a number that combines enthalpy and entropy. It brings the two together mathematically. Thankfully, we finally have an abbreviation that makes sense. I know, right? Enthalpy is H. That doesn't make sense. Entropy is S. That doesn't make sense. Finally, Gibbs free energy is G. Just when you'd lost all hope. But guys, how then does Gibbs free energy bring together enthalpy and entropy? And guys, the answer is this. Gibbs free energy is simply equal to the enthalpy of a system minus the entropy of a system times its temperature. But guys, because this is a chemistry class, rather than talking about systems, we tend to talk about processes. So we deal with these in terms of change. And this is the equation that we're going to be working with. That delta G, the change in Gibbs free energy, is equal to delta H, the change in enthalpy, minus T delta S, the change in entropy. And guys, if you want to look, I don't know that you need to. This is on your AP equation sheet. There it is. Did you guys find it? If you want to look, it's there. So guys, here's what we're going to do. We are now going to take this idea of Gibbs free energy and we're going to use it predictively. But before we do, we need to tie it to spontaneity. So guys, this then is the deal. The sign of delta G is finally then the gold standard predictor of spontaneity. Guys, if you want to be able to say, and you do, if you want to be able to say with certainty that a reaction is spontaneous, then guys, it's not just delta H, it's not just delta S, it's bringing the both together. And that's what delta G does. So guys, delta G is actually finally the thing that will tell us if something is spontaneous. So what do you suppose the value for delta G is going to be if something's spontaneous? Positive or negative? Think about how this works. So guys, I'm going to go to a pen. So let's talk about delta H. What kind of delta H values are spontaneous? Positive or negative? Negative, right? Because what does that mean? Exothermic. What kind of delta S values are positive, right? That means what? What does it mean if delta S is positive? It means disorder is going up. Okay, so let's look. So here's what we know. We know that delta G is equal to delta H minus T delta S. And we've identified that negative delta H's tend to be spontaneous. Positive delta S's tend to be spontaneous. Now guys, here's the trick. What does T represent? In Kelvin. So guys, if T is in Kelvin, what can temperature never be? Negative. So here's what we've got. Negative delta H means spontaneous, exothermic. Positive delta S means spontaneous, disorder goes up. Temperature can never be negative because it's in Kelvin. So guys, if this is negative and this is positive and this is positive, what kind of values will this always generate? Negative, because you've got a negative number minus multiplying two positives together is positive, so you've got a negative minus another number. That will always generate negative numbers. So now let's come back to the original question. Guys, what values for delta G guarantee spontaneity? Negative values. And we just demonstrated that based upon what we already know about enthalpy and entropy. So guys, bottom line is this. If delta G is negative, the reaction is spontaneous every single time. This is the only way that you can guarantee spontaneity is figure out delta G. Actually, there's another way to do it with batteries, and we'll talk in chapter 20. But, guys, for us right now, the only way to guarantee spontaneity is if delta G is negative. Go ahead, Mark.
Okay, so I just need to
All right. Yeah.
So when entropy goes up, when it's a positive number, does it release energy or?
Yeah, so what we're saying is, so...
Is it just like entropy by itself?
Yeah, so, but I understand the tension, right? So the idea is this. In our universe, things tend towards greater disorder on their own. And as they do, think about if we were to bring that back, right? If we were to take something that was disordered, like the egg, and it was kind of stupid, but like the egg, if we want to bring that back, we've got to add energy and do work, right? So when something becomes disordered, it falls and goes splat. It's releasing energy, as Doug got us thinking. It's releasing energy in the form of disorder. So a positive delta S is a net release in energy, because we've got disorder going up and our universe heads towards that spontaneously. Is that okay? Does that settle okay? You guys okay with that idea? So guys, if you understand what we're talking about now, here then comes an interesting question. Guys, are you settled with this idea that if delta G is negative, the reaction's spontaneous? What about this? What would it mean if delta G is 0? What does that mean if delta G is not changing? Equilibrium. And what do we call that? A reversible process. So guys, if you have a system that is at equilibrium, no net change in Gibbs free energy. And actually, Susanna, that's where that really weird answer to question number whatever was, where we said it's the heat if you were able to reverse it. That's actually the math behind this, because if it were reversible, if you could push it backwards, the entropy change and the heat change would be equivalent, making delta G 0. Yeah. Yeah, and that's the point. So for it, because that, and I don't want to dig into it much, but that's actually where the answer in the back of the book came from, is the idea that if it could be reversed, it would be reversible, and then the energies would be, that's what they were getting at. So don't get too much into it, but that was the idea. So guys, what about this? What does it mean if delta G is positive? It means it's not spontaneous, but guys, the trick is this. It is not spontaneous in the forward direction. So the way that we're representing the process, if delta G for the process is positive, it means it doesn't go this way on its own. But you know what it could mean? It goes the other way on its own. Because what happens if we flip a reaction around? We change the sign of the energy and the entropy changes. So guys, if delta G is negative or positive, the reaction is not spontaneous in the forward direction. But it could just be that the reaction's going the other way. All right, so we are here. So guys, we okay with this idea of delta G? This is where this gets interesting. We're gonna play a little game. So guys, if you understand the concepts behind delta G, what we're gonna do now is we are going to tie this thing. Just a second, it should have skipped this. We already talked about that. So guys, what we're gonna do now is we're gonna tie this thing to spontaneity given conditions. And guys, this is the stuff that they like to pick at on the AP test. So guys, do this with me in your notes. So here's our Gibbs free energy equation. And here's what we've got. in this equation, we have got a free energy term, and then we've got delta H, which is an enthalpy term, and then we've got negative T delta S, which is our entropy term. So Gibbs free energy brings together enthalpy and entropy. Now guys, I'm thinking you don't need to write this down given what we wrote on the board a minute ago, but let's make sure you're clear. So guys, when we talk about enthalpy, our enthalpy term, when we talk about enthalpy, what values for delta H tend towards spontaneity, positive or negative? Negative, right? So positive values are endothermic, negative values are exothermic, and it's the negative values that tend to be spontaneous. Is that okay? Okay. So guys, what about entropy? So what values for delta S tend to be spontaneous? Positive. But guys, the math is a little weirder than that because it's a positive times a temperature, which is always positive, but then times a negative sign, which makes the entire thing negative. So guys, the thought goes like this. So if T is always positive, when S is positive, right, that means it's becoming more disordered, negative T delta S will be negative. Does that make sense? And then similarly, if delta S is negative, which means disorder is going down, then negative T delta S will be positive because temperature is always positive, and that can be thought of as a -1. You guys okay? Because guys, we're about to play a game. Here's what you're going to do. So guys, we now have 4 possible combinations. I would encourage you to write this down in your notes. Guys, we now have 4 possible combinations. We have got an enthalpy value and we have got an entropy value. Enthalpy can be positive or negative. Entropy could be positive or negative. Or we could have one of each. Here's what I want you to do. As you write this thing down, what I'd like you to do is this. Columns. Create a column underneath delta H and create a column underneath delta S, and then perhaps we can separate it this way into 1, 2, 3, 4. Sorry, this is kind of trailing down the board. 4 different spaces. You know what? We could even write over here a little bit. And I'm going to say that differently. And then over here, we're going to create another column that asks the question, EOUS, is it spontaneous? I've never taught this way. This could be good. Or it could be horrible. We'll see. I think it'll be good. I'm experimenting on you. So guys, here's what I want you to, did you all get to kind of draw this? Here's what I want you to do. Over here, I want you to write down, please, in here, and this isn't a space, this is just, so here and here, what values for delta H and what values for delta S guarantee spontaneity every single time? I put them in, just write them in, plus positive or negative. So guys, what values for delta S and what values for delta H guarantee spontaneity? So let's talk. Guys, what values for delta H guarantee spontaneity? Negative values. And what values for delta S guarantee spontaneity? Positive. So guys, if enthalpy is negative, change in enthalpy, and if change in entropy is positive, that will always be spontaneous, because what types of delta G values will that always create? Negative values. Now guys, do this. Under what delta S, delta H situations, will this never be spontaneous? Fill in the values. So what about delta H? Positive, because what does that mean? Endothermic. It's taking in energy. That doesn't favor spontaneity. Guys, what about delta S? Negative, right? Because what does that mean if delta S is negative? What's happening to entropy? It's going down. Disorder is going down. So guys, what we're describing right now is a reaction that sucks in energy and organizes stuff. Does that happen on its own? Heavens no. So guys, what kind of delta G values will this always produce? Positive values. And those will never be spontaneous. Yeah.
So you said that like they can switch to.
And that's the point. Yeah. So imagine what we just said. What we just described is a process that takes in energy and organizes stuff. And that doesn't happen on its own. But the opposite could. We could have a process that gives away energy and screws stuff up, which would be the opposite, right? So as it's written, it's never spontaneous. But the reverse would then be spontaneous. Does that make sense? Okay. So now, guys, you see where this is headed, right? What about this? And you know what? Let me... so what if we had a system where both of these are negative? Or what if we had a system where both of these are positive? Here's the $100 question. Are they spontaneous? Either one of them. Depends. The answer is sometimes. What does it depend upon? Temperature. And guys, this is where this gets really interesting. Here's the idea. If enthalpy is negative, does that favor spontaneity? Yeah. So this, and I think of it this way, this is good. This is favoring spontaneity. A negative delta H is good. That favors spontaneity. Guys, what about a negative delta S? Does that favor spontaneity? What does it mean? Disorder is going down. That's bad. That does not favor spontaneity. So guys, if we want this reaction to be spontaneous, what do we have to do? Well, we've got to minimize the effect of bad. So how do we minimize the effect of this bad entropy issue? We lower the temperature. So this would be spontaneous at low temperatures because that takes that entropy term and decreases the effect that it has on the process. Now guys, let's look at the other one. What about a positive delta H? Does that favor spontaneity? No, that's taking in energy. Now this is bad. What about a positive delta S? That's good. That does favor spontaneity. Now guys, the $10,000 question becomes, what is this? When would this be spontaneous? Well, now we need to magnify the impact of this entropy change because that's favoring spontaneity and we want that to be all the more significant. So how do we do that? Raise the temperature. And so guys, this would be spontaneous at high temperature. So guys, before we ask the question that I pray is rattling around in your brain, guys, look at the table at the bottom of 809. Do you see it? Guys, what we did is just recreated this table. Do you see the connection? So delta H, delta S, we went negative, positive. That's always spontaneous. Then we went positive, negative. That's never spontaneous in the forward direction. Then, guys, we went negative, negative. We said that's spontaneous at low temperature. And then we went positive, positive, and we said that's spontaneous at high temperature. Do you see the connections? So what then is the question you guys are dying to answer? Somebody's got to be thinking it. Go ahead, Mark. Go ahead.
So you always have to have that constant temperature, since it's not changing.
No, but in order to solve this, it doesn't have to be a constant temperature, but it has to be a known temperature, right? We have to know, and in that sense, it can't be changing, but we have to know the temperature in order to figure out the spontaneity. Is that okay? Go ahead. Guys, what does low and high mean? Spontaneous at low temperature. Is that like the temperature of a black hole? Or is that like the temperature in your refrigerator? What does it mean that and black hole's a bad idea, they're actually hot. What I meant to say was like interstellar space where there's nothing. So guys, what does it mean to be cold? What does it mean to be low temperature? What does it mean to be high temperature? Well guys, it turns out that you need to be able to calculate this. What does it mean to be a high temperature system? And what does it mean to be a low temperature system? And guys, the answer is different for every chemical process. So the question we need to answer then to wrap up the day and the unit is, what does it mean? Where's that break between high and low? Spontaneous at high, spontaneous. Where's that break for any particular system? How could you figure it out? How could you figure out where the breaking point is? Go ahead, listen. Okay, so we need to solve for T, right? But if we're going to solve for T, we need some information. We need delta S, we need delta H. We are going to solve for T, but there's an underlying piece of logic that allows us to solve.
Well, we want G to be negative, so then we need H to minus T.
Good. Okay, so let me track that down. So if we're looking for the temperature range of spontaneity, we want G to be negative. So we're looking for values at which G is negative. But that's impossible to solve for because depending on the negative number you plug in, you could be chasing your tail forever. Do you see what to do?
So it has to be with T times S is less than, it's more than H.
Good. But again, that could be in an infinite number of cases because it could just get more and more and more and more negative. So how do we find the tipping point? Go ahead, Susanna. Which would make delta G what? 0. Guys, that's what you do. And Levi, I think if you'd had enough time, you would have got there because your logic is perfect. But the idea is this. What we do is we set delta G equal to 0. That's the point of equilibrium. And then we figure out on which side of that, we solve for T, and figure out on which side of that does the reaction then become spontaneous. So guys, let's solve one of these together, and then we will... we'll dig into some homework. So let's do this. Let's try... There used to be one of these in... Oh, they took it out of our book. There used to be a sample exercise where we solved one of these. Interesting. Is it not there? Oh wait, what about this? Oh, they took it away. That's very, very sad. So guys, let's do this then. We're just going to make something up. So guys, fictitious process where, that is a horrible color, where A plus B becomes C and D. And let's do this. Let me give you some data. So delta H for this process is negative 10 kilojoules per mole. And then delta S for this process is negative 325 joules per mole Kelvin. So guys, the question then becomes this. In what range of temperatures is this process spontaneous? So how do we figure that out? Where do we start? We need an equation. So we're going to go delta G is equal to delta H minus T delta S. And now guys, what are we going to set G equal to? 0. And they gave us delta H, negative 10 kilojoules per mole. And then that's minus, and we're solving for T. And then our delta S is negative 325 joules per mole Kelvin. And we now solve that for T. Yeah, guys, if you solve this, just forget it if this were on the AP test. Guys, this is not okay. And I know Mark saw it. Maybe some of you did as well. Guys, the units don't match. You can't subtract joules from kilojoules. They have to be the same. So my suggestion to you, and this is just me, if you want to go the other way, you can. I find it much easier to convert joules to kilojoules than I do kilojoules to joules. And here's why. If you want to go kilojoules to joules, I'm just going to make a mess. You've got to add 3 zeros to it. And that just creates problems. What I find a lot easier is just to convert joules to kilojoules, because then all you got to do is put decimal right there and make that kilojoules. Now we can solve this. So what we need to do then is we need to add 10 to both sides. So we can do this now. Kilojoules drop, moles drop with our amounts, and we're just left with Kelvin, which will eventually be our answer. So guys, we've got negative 10 well, those are gone. So we've got negative 10. What's that? I can't even do algebra. So 10 is equal to negative, which then becomes positive because our value is negative. So positive 0.325 over Kelvin, which then when you do the math gives you the units Kelvin. So guys, we're going to take 10 and divide it by 0.325. And the temperature is, I got 31. Did you as well? Why is this positive? Because this is negative and it's a subtraction. So a negative times a negative is a positive. So it would be negative and then T, and then solving for T. Guys, you're swatting at gnats and choking on camels. Here's the important point. This isn't the answer. Yeah, it's asking for a range. So what does 30 tell us? That's the temperature at equilibrium. So guys, this is not the answer. The question was not at what temperature is this process at equilibrium. The question was what? At what temperature range is this reaction spontaneous? So we need to include 30, but that's only part of the answer. On what range is it spontaneous? Above or below that? Well, let's think through it. Negative delta H, does that favor spontaneity? It does. Negative delta S does not. So guys, that means that our entropy factor is fighting against spontaneity. It's bad. So if our entropy factor is fighting against spontaneity, what do we want to do? Diminish it. So at what temperature range would it be spontaneous? less than 30 Kelvin. So guys, the idea then is that we would say this reaction is spontaneous at any temperature less than 30 Kelvin. And it's not inclusive. It's not 30 Kelvin and lower, because at 30 Kelvin, it's actually at equilibrium. So guys, oh, go ahead.
Does every reaction have a point
Does every reaction have a point at which it's no longer where it switches?
Yeah,
Is that what you, and the answer is yeah, it does. And actually there's an interesting question in the homework where they're drawing graphs. Maybe you saw that and said, wait, I can't do that yet. There's a question in the homework that addresses it. Okay, so guys, one little thought here, because I'm going to see this on the test. I feel compelled to warn you. Guys, if you do this math, and if your temperature ends up negative, it can't be. Why not? Because it's a Kelvin temperature. So guys, if you do this math and your answer is negative, you know you've done something wrong. You guys okay? Okay. So guys, with that said then, this is, again, back to your homework. You've already seen this. But we're going to spend the remainder of the day today and work on this. Some of you, however, need to go next door and gather